Xander, you can go ahead and go off. Okay, we'll give it a second for people to come on in. My dog being the soundtrack in the background. Okay, guys, we're going to jump on in. Welcome to Troubleshooting Search and Retrieval, enhance performance with powerful AI solutions. My name is Amanda Wagner. I am the Senior Community Manager at Pinecone, and we are absolutely thrilled to have you here. For those of you who may not be super familiar with Pinecone, Pinecone is a vector database that makes it easy to build high-performance vector search applications. Way more to come on that. But before we dive into today's content, I want to go over a few basic housekeeping rules. Number one, we ask that you use the chat for chat. Go ahead, say hello, let us know where you're coming from, let us know what you're building and why you're here. We want to hear from you, but when you have a question, we ask that you ask all questions in the Q&A portion of the Zoom. This helps us to get to everybody's questions when it comes to the Q&A. So again, chat and chat, questions in the Q&A portion of the Zoom. If you miss something, no worries. This event is being recorded and we will share it with you via email after the event. We also share all of our previous events on YouTube, on our social. So if you have not followed and subscribed, I highly suggest you do so now. In that same email, we will be sharing a post-event survey. It takes 5 seconds, helps us let us know what we're doing right, what we can do more of, and gives us just additional ideas to bring you guys great content. Have any questions after the event? Go ahead and ask them in the Pinecone forums. You can find that on our website under community. Now, without further ado, I am going to hand it over to Xander to tell us a little bit about what we're going to be learning today. Xander, take it away. Xander, you're on mute. Has to happen once, at least every webinar.
Can everybody hear me? Awesome. Thank you, Amanda. Awesome. I'm going to share out my screen. Looks like I am. Can people see my screen here? Thumbs up. Awesome. So let's go ahead and start the slideshow. Thank you so much for joining us today. My name is Xander. I'm a developer advocate at Arize AI. And today we're going to be talking about how to troubleshoot your search and retrieval applications. And with me today, I also have Lance Martin from LangChain and Kevin Butler from Pinecone. Lance, do you want to give us a brief intro to yourself?
Yeah, sure. Great to be here and see all of you. I'm at LangChain, as mentioned. Prior to that, I spent a lot of time working on applied AI in the self-driving car industry.
Nice. And Kevin, can you tell us about yourself?
Sure. Hi, everyone. My name is Kevin Butler. I'm a customer success engineer at Pinecone, and a part of my role is to help customers onboard, enable them from a technical standpoint. And I've been in the search space for several years now, both from a lexical and a semantic search perspective.
All right. Very good. Thanks, Kevin. So let's go ahead and kick off the presentation. I'm going to start out just by giving you an overview of our agenda. We're going to start out, and Lance is actually going to just talk about what is search and retrieval, how does it work, and he's going to give us an introduction to LangChain. Then Kevin's going to talk about Pinecone, and then we're going to actually get into the LLM deployment stack and start talking about what can go wrong when you're deploying search and retrieval applications. And after we've done all that, we're going to hop into an interactive workshop where we're actually going to detect some issues with a search and retrieval application and identify the root cause of the issue using an open source project called Phoenix from Arize. Okay, so without any further ado, I'm going to kick it over to Lance, and he's going to tell us more about search and retrieval in the context of LangChain.
Thanks a lot. Well, first and foremost, maybe it's good to introduce LangChain, which is an application development framework for language models. And one of the most popular use cases for LangChain is this retrieval augmented generation flow shown here, in which you typically start with some documents. It could be your data, it could be public data, YouTube, Twitter, it could be storage. We have over 80 integrations with various data sources. And this allows you to pull kind of data into the world of language models and language model applications. Following that, typically we perform splitting. This is due to kind of the need to store smaller sized chunks in vector DBs, typically because of the LLM context window. We'll talk about that later. But in any case, typically you're starting with sources from some large number of possible integrations, splitting them, storing them. Of course, Pinecones we'll talk about as one of the primary kind of vector DBs. And then there's this retrieval step. And basically what you're doing here is you're asking a question to the model, for example, asking a question about your documents, and it's going to retrieve from your storage source, i.e. your vector DB, relevant chunks to your question, pack those into the prompt and pass those to the language model. And that's really the flow that we'll kind of be talking about a bit today. And LangChain, as mentioned, has a lot of integrations across this flow. Over 80 on the document kind of connector side, over 30 integrations, including Pinecone for storage and retrieval, and then over 40 different integrations for language models. You can use to synthesize those final answers. Maybe next slide. Of course, one of the challenges here is kind of the paradox of choice. You have many different options across this stack and many different parameters, which kind of motivates the need for evaluations, which I think Xander's going to talk about a bit later, as well as we've had a lot of questions over time about answer quality. How did you store and embed these text chunks in your vector DB, but how do you actually kind of troubleshoot when you have kind of strange or low quality answers? How do you kind of go back and debug your embedded texts and how they relate to your answer or your question? I think Xander's going to provide some nice demonstrations there, and I'll hand this over to Kevin to talk about Pinecone, which is one of our primary storage integrations in Pinecone.
Thank you, Lance. So Pinecone, as Amanda already kind of defined for us, is a core component as part of all of this process. Of course, with any GPT style application, whether it's a chatbot, whether it's semantic search, or in a variety of other use cases, vector databases allow us to store that data in a very explicit way. And actually, Xander, next slide. When we talk about vector databases, what we have below here is 4 different types of custom databases, if you will. So we typically are familiar with key value stores. We understand document stores, such as your Elasticsearches and other traditional search engine style document stores. And then, of course, we have graph databases, and then finally the vector database. So Pinecone was built purposefully and specifically for vectors from the start. So it is designed to be an efficient and scalable database. Next slide. And you're probably going to see a similar image to what we show here on the right-hand side. This is a typical GPT style, Q&A style, chatbot style application where you have your data on the left-hand side. We use an embedding model to create the embeddings from your data and store that into Pinecone. And then if we start to work from the right-hand side, we see the application that can make a query also needs to be vectorized and then queried against Pinecone. Once we get the results from Pinecone, that becomes part of the context and also part of the prompt that will ultimately go to the AI model. Next slide. Okay, so for Pinecone, why choose Pinecone? Of course, the first and foremost, again, it's purposefully built as a vector database first. And then as you are making your choices on a vector database, there's a lot of options out there, anything from databases that you can run on your laptop to a server to a large scaled vector database such as Pinecone. We're able to offer large scale at low latencies. The ease of use is one of our favorite parts of our product, in that the developer experience is very good, very satisfactory as far as being able to use the simple API, as well as our Python clients. And we have a couple of other connectors as well, or clients. It's easy to operate, it's easy to scale, and at large scale, it is low cost, and we essentially scale it to the size that you need, and then the cost effectiveness is there as well. In the meantime, I would recommend that you visit us at app.pinecone.io to actually sign up for a free account, no credit card required. That way you can actually use the API, you can use the database for development purposes and experimentation and evaluation, and see how you like it. Next slide. However, the story doesn't end here, actually. So LangChain is an extremely powerful framework. We use it a lot in-house. We wrote a huge YouTube series all about LangChain. So I definitely do recommend it. And in fact, the link is right there. And then finally, of course, the app.pinecone.io. Again, try that free account, no credit card. And we are that enterprise ready solution to serve your production scale application. But ultimately, the next question that we might be asking ourselves, and I'm going to hand it back to Xander, what if our solution still isn't producing high quality results?
Awesome. Yeah, so thanks, guys. So as Kevin mentioned, the workshop that we're going to be getting into is actually debugging issues with search and retrieval, detecting issues as they happen, and actually pinpointing the exact mode of failure. And we're going to get into all of that. We're going to get into the details, and you're going to actually have the opportunity to run a notebook where you're going to do all of that. But before we dive into the details too much, I still want to keep it a little bit high level at first. So Lance gave you the what. He gave you how does search and retrieval work? What is it? But let's also just backtrack for a minute, and let's talk about, why do I need search and retrieval? Why are we going through all this trouble? And to illustrate this idea, I'm gonna take you to ChatGPT. If you go to ChatGPT and you ask ChatGPT, tell me about Arize, the response that you're going to get back is going to be, I'm sorry, as of my knowledge cut off in September 2021, I don't have any specific information on Arize. So it turns out Arize is a little bit too recent in order to be in the training set for ChatGPT. ChatGPT doesn't know anything about Arize. But if you were to go to the Arize AI documentation homepage and copy and paste our documentation into ChatGPT and then ask ChatGPT, tell me about Arize, ChatGPT is going to give you a really nice answer. It's going to say, Arize AI is a real-time machine learning, ML observability, and explainability platform. Okay, so why do we need search and retrieval? Well, there's a couple of reasons. Search and retrieval, first of all, allows you to provide your own context and provide your own data to give that information to a large language model to synthesize a response. And this can be useful, for example, if you're dealing with documentation that's constantly changing, or if you're dealing with a proprietary data set that a large language model like GPT-4 was never trained on. The second reason is that search and retrieval allows you to ground your responses in trusted sources of information. So you can give it a piece of documentation that you know is correct, and that just increases the chances that the LLM is going to produce good, high-quality output. And again, I kind of talked about this already, but the third reason would be it's really easy to just swap out documents from your knowledge base and from your index, easier than fine-tuning an LLM, for example. So that hopefully explains why you might want to use search and retrieval. And now let's actually start talking about the various kinds of problems that can arise when you are using these kinds of applications. So what we have in this diagram is a really high-level picture of the simplest possible question answering service that you could use with an LLM. In this service, the user over here on the left is just going to send some kind of question to the service. That question is going to be sent to a foundation model provider, such as OpenAI or Anthropic, which is going to produce a response, which is then sent back to the user. And ideally, you would have some kind of thumbs up, thumbs down button, or some other mechanism to actually get user feedback to figure out, was this a good response from my service? And even in this very simple picture, there's already a couple of problems that can arise. The first problem being that some of these LLMs are prone to hallucination. They can make up information. They can give you inaccurate information. And the second problem is that evaluation is actually really difficult. Even if you're fortunate enough to get that user feedback from your user, to get that thumbs up or thumbs down signal from your user, pinpointing the exact reason and getting to an actionable next step to improve your service can actually be very difficult. And the picture just becomes more complicated when you add in an additional step of search and retrieval. So once again, what we're doing here is we are taking that user query, embedding the query, retrieving relevant documents, and then enriching our prompt with context from those relevant documents in addition to the user query, which is then being sent to the LLM. And this introduces an additional possible failure mode, namely, we might retrieve the wrong context. And this is where Arize is going to come in. We are going to offer you LLM observability, which just means that we're going to provide this foundational layer that is going to allow you to detect issues when they arise and quickly identify the root cause of the issue. So let's dive in a little bit deeper. I'm going to dive into this particular box, and we're going to unpack what it means to get bad retrievals. And we're going to keep running with this example of the Arize documentation because that's actually the exact data that we're going to be working with today. In the workshop portion of this talk, we're actually going to be debugging a chatbot over a knowledge base containing the Arize docs. So let's run with this example for a minute. When you create this indexed knowledge base, what you do is you take the Arize documentation, you chunk it up, and you store it in Pinecone. And then you're going to have users ask questions of your question answering service. So one question that someone might ask is, what's the price of Arize? And it turns out that there are a couple of different ways that a query could go wrong. In our particular case, as you're going to see, we don't actually have any information in our documentation about pricing. So the first issue that could happen is maybe I don't have any similar documents. Maybe I don't have any relevant documents to retrieve from my knowledge base. And so it's not actually possible for my chatbot to answer the question because it doesn't have the information that it needs. So one of the things that we're actually going to show you how to do is how can I identify areas of user interest that my knowledge base doesn't cover so that I can go augment my knowledge base. But there's a second mode of failure that can happen, which is that even if you have information about the query, even if you have documentation around the pricing, for example, sometimes the retrieval step just fails. Sometimes, even though you're retrieving the most similar documents by cosine similarity, maybe they're not actually relevant to the question. And so you're actually feeding irrelevant context to the LLM. And again, if you feed in bad context to the LLM, you can't expect it to give you a good response. So these are the two particular modes of failure that we're going to be investigating today. All right. Very good. So now we're going to hop into the demo portion of the workshop. But before we actually jump in there, let me just explain to you what we're going to be using. We're going to be using a tool from Arize that's called Phoenix. It's relatively new. It was open sourced about 2 months ago or so. And again, you can just pip install it with pip install Arize-Phoenix. What Phoenix is an application that runs in your notebook environment. So today, we're actually going to be running Phoenix on your Colab server. You could also run it on your local laptop or anywhere where you can run a Jupyter notebook. And what Phoenix does is it helps you detect issues with your machine learning models and your LLM applications. And again, it helps you pinpoint the mode of failure, find the root cause of the issue. And what kinds of issues are we talking about? Well, there's a lot of different applications that you could use Phoenix for, but the use case that we're dealing with today is a search and retrieval application built with LangChain and Pinecone over the Arize documentation. Okay, so hopefully that's clear so far. And you're going to have the opportunity to follow along. So here's a link. I'm going to drop this in the chat. So let me open up the link. Here's the Colab that we're going to be running today. And I am copying and pasting that into the chat if I can find it. Here we go. Okay. So that's the full link. If you want, you can also just use the bit.ly though. It's https://bit.ly/arise-langchain-pinecone-collab. Okay. And before we actually dive into the notebook too much, I want to show you the cool part, right? So this is where we're heading. This right here is Phoenix, and I'm actually running it on my laptop right now. And what you're seeing in this view is actually a low-dimensional representation of our embeddings, our query embeddings in blue, and our database entries or our chunk embeddings, the documentation chunk embeddings in purple. And if I actually just circle a cluster here, let me look for a good area of overlap. So I'm seeing this area right here where I'm seeing a little bit of overlap between some of the blue and the purple points. Let's just take a look at what these points actually represent. So again, these blue questions are user queries. One example of a user query is, do we have the ability to resolve a monitor? Okay, so that's a question that someone might ask of our search and retrieval application. And yeah, a little bit of context too. Monitoring is one of the things that Arize offers. So this is a user asking questions about the Arize platform. It looks like all these questions are about monitors. And here in purple, you can actually see some documentation, some chunks of documentation. And you can see that the documentation is also about monitors. So what does that tell us? It just means that we have reasonable embeddings that are embedding semantically similar pieces of text nearby in the embedding space. And we're going to dive into how you can use this visualization in just a moment. But let's actually return here to the notebook. So this notebook is pretty long. It's a little complicated. In order to actually run it, all the cells, what you need to do is come here and click on this script. And this is a script that is actually going to build you a Pinecone index using LangChain of the Arize documentation. And I'm not going to go over how to run this script in this particular workshop. I'm going to assume that if you want to run the notebook, you should just go ahead, run the script at home. And to do that, you're going to need to go to pinecone.io, create a Pinecone account, create an OpenAI account, get your OpenAI key, and just run the script. And then you will wind up with this Pinecone database full of documentation chunks from the Arize documentation. So for this workshop today, you'll notice that a lot of these cells have these red exclamation points ahead of them. For any cell that has this red exclamation point, go ahead and skip that cell. Those are the cells that require your OpenAPI key and your Pinecone API key. So skip those cells, but you'll see a lot of the cells also don't have those red exclamation points. So go ahead and run those cells. Just run the ones without the red exclamation points all the way down. And then you will wind up inside of Phoenix at the very end. So for me, I'm going to do something slightly different though. I'm going to actually copy over my Pinecone API key. I'm going to copy over all that information. Let me grab it real quick, just so that you can see what this would look like once you've actually built your Pinecone index. So I'm going to first of all grab my Pinecone environment and paste it in here. I'm going to grab my Pinecone API key, paste it in here. I'm going to grab my Pinecone index name, which I think is called Arize-docs. And I'm going to grab also my OpenAI API key. And in general, I would advise you not to do what I'm doing right now, which is to share all of your private API keys, but just remember to revoke them afterwards if you do. Cool. All right. So let me see. I've got my OpenAI API key. I've got my Pinecone information here. At this point, I should just be able to run all. So I'm going to run all, and I'm going to let the notebook run. And for this particular notebook, you don't need a GPU. And while that's running, let me just check. Looks like it's going. While that's running, I'm going to dive into the particular chatbot architecture that we're dealing with today. So this is the chatbot that we've built and that we're dealing with. The purple component, or the purple part of this diagram, is the LangChain and Pinecone chatbot. And the blue part of this diagram is the foundation model provider, in this case, OpenAI. And I'm going to walk you through the 5 steps that we've got here that take the user from asking a question to receiving a response. So in step 1, the user asks a question. And again, for this particular chatbot, this is a chatbot over the Arize documentation. So it's going to be probably some kind of question related to the Arize platform. And the very first thing that we're going to do is we are going to use a LangChain component called OpenAI embeddings. And what that's going to do is it's going to make a request to the embeddings API for OpenAI in order to embed the user query, and it's going to get back the embedding for the user query. And this particular chatbot data that we're dealing with is using the text embedding ADA2 model. In the second step, or in the third step rather, we're going to take that embedding that we just computed for the query, and we're going to run a similarity search across Pinecone. And what that's going to do is it's going to look for the 2 most similar pieces of context in our vector database by cosine similarity. And that is what is being returned over here. So again, context 0 and context 1 are just chunks of our documentation. You can think of it as a paragraph of documentation. In step 4, we're actually going to generate the response to the user. And the way we do that is we take the user query and we take the retrieved context. We're going to format it into a single prompt. The prompt is going to say something to the effect of, here's a question from the user, here's some documentation, answer the question using the documentation. And we're going to send that prompt to the chat completions API. In this case, we're using GPT 3.5 Turbo, and that's going to actually generate the final response, which is then returned to the user. So hopefully that is clear at a high level what the chatbot architecture looks like. And you can actually, if you come back to the notebook, you can actually see some of these components right in this cell right here. Here we go. So you can see the embedding model name. You can see the actual OpenAI embeddings here. You can see where we're doing the document search over Pinecone. And this is where we actually define the LangChain chain, which is going to be doing the user query. And in this particular case, has this already run? Yeah. So in this particular case, I'll show you what it looks like when you actually get this whole thing running. We've got a piece of query text, and the query text is a user asking, how do I get an Arize API key? Okay, so that's a pretty natural thing that someone might ask of our documentation. And you can see that we actually run this command, chain.run query text, and that is running all of the steps that I just went through in that previous diagram in order to get a response from the user. And that's what we see here. So the response is, this is, again, the response from this chatbot. It says, to get an Arize API key, you need to click the Get Your API Key button on the top right of the Explorer page, which will generate your API key, et cetera, et cetera. And the other things that we're also recording here are things that are relevant for Phoenix. Things like the first piece of retrieved context, the similarity score to that first piece of retrieved context, the second piece of retrieved context, the second similarity score, and the embedding from the query from the user. Okay, so hopefully that's pretty clear so far. Next step is we are going to talk about the data. So again, I don't want to dive too deep into the details of the notebook. The notebook is pretty complex, but basically the TLDR here is we're trying to get your data to look like this. This is basically what the whole notebook is about. So the first thing is, let's go over what does our database data look like. Again, this is the data from our knowledge base. So our knowledge base, it really is quite simple. It consists of chunks of documentation. So here's an example. This first one says, to get started quickly. To get started quickly, you can use the scripts provided with the distribution, extract the tar file provided by the Arize team, et cetera, et cetera. And then here's the actual embedding vector that is being stored inside of Pinecone. So that's what the database data looks like. And here's what our query data looks like. Each query is, again, going to have a piece of text, just the question asked from the user. In this case, the user is asking, how do I use the SDK to upload a ranking model? Once again, a question that someone might ask of our documentation. We've got the associated embedding vector for that query. We have the context, the similarity, And the second piece, the response from the user or from the chatbot here. So the chatbot responded, to use the SDK to upload a ranking model, you will need to first install the SDK, et cetera, et cetera. We've got user feedback. And again, user feedback in this case is just going to be thumbs up, thumbs down. So a +1 means the user gave this response a thumbs up. A -1 means the user gave the response a thumbs down. And then we're going to get into these last two columns in a moment. Okay, awesome. So now that we've gone over what the data looks like, I'm going to see, it looks like my collab is run. So I'm going to scroll all the way down to the bottom of the collab, and I encourage you to do the same. Scrolling all the way down to the bottom of the collab, you see this link right here. To view the Phoenix app in your browser, visit this link. And again, Phoenix is just an application that's running, in this case, on this very collab server. So now we're going to get to the fun part, which is actually using Phoenix to debug your application. This just takes a minute. And what you're seeing here is the Phoenix homepage. And the first thing I'm going to do is I'm going to click here in the embeddings section. I'm going to click on centered text vector. And that's going to bring me back to that page, that embeddings view that I showed you a couple minutes ago. So right now what's happening is we are actually taking those high dimensional embeddings that we just defined in our notebook, and we're reducing the dimension down to 3 dimensions so that you can see them. And this is what you see. And so again, what you're seeing are query data points, query embeddings in blue, and database entries or knowledge base entries, chunks of your documentation in purple. And it's spinning around. That's pretty cool. But let's actually, let's see what we can actually do with this. Like, what value can you actually get out of this, right? I'm going to tell you a couple of stories here. Let me go back to the slides for a minute. I'm going to tell you a couple of stories about the kinds of questions you can answer using Phoenix. So the first story is, how do I catch bad responses? And let's suppose for a minute that I have some user feedback. I have a thumbs up or a thumbs down signal from my users that's telling me, hey, this is a good response, or hey, this is a bad response. How can I actually visualize those responses and understand them in a meaningful way? So let's do that. Let's hop back into Phoenix. And the first thing I'm going to do is I'm going to call your attention to the display section down here in the bottom left corner. And you'll see that there's this color by dropdown. And in the color by dropdown, let's go ahead and select dimension. All a dimension is think of it as a field of your data. And the field of my data that I care about right now is user feedback. Okay. And let me pull this up a little bit so we can see it. And what you're seeing over here now in the point cloud is, let me toggle off the database entries for a minute. What you're seeing are the queries, only the queries right now. And the purple queries are the ones where our users have given a thumbs down to the response from the chatbot. Our green queries are the points where our users have given a thumbs up to the responses from the chatbot. And there's also some gray points in here which just didn't get any response from the user. So if I care about where are my bad responses, what kinds of questions are my users asking where the chatbot is producing responses that get thumbs down, like if that's what I care about, what you can do is you can come up to this metric dropdown up here. And once again, let's just select user feedback. And you'll notice that these clusters over in the left actually just flipped around. And maybe I should actually explain these a little bit, right? Once we actually reduce the dimension of your embeddings, what we do then is cluster in this low dimensional space in order to surface up meaningful groups of queries in this case. And let's go ahead and sort these clusters by lowest metric value. So what that means is that now the clusters here are being sorted in ascending order by the average user feedback. So you can see that this cluster is up at the top, meaning this is the most problematic cluster because it has an average user feedback of -1, which means that every point in this cluster got a thumbs down. So let's take a look at this cluster. All right, so again, here's the cluster right here. And the points in the cluster are here. And again, I did a little bit of foreshadowing earlier, but some of these the topic here, or the theme of this cluster, should be pretty familiar. How much does the Arize platform cost, and how do you charge? Is there a cost for Arize beyond an annual subscription price? What's the difference between Arize's Pro and Enterprise plans? How much does Arize charge? Okay, so all of the questions in this cluster are around cost. And again, you can see that all these purple ones are the ones where people gave it a thumbs down. They gave the response a thumbs down. And you can notice something really interesting here, which is that even though I've already told you, like we already know, that we don't have any pricing information in our documentation, even though that's the case, you'll notice a few of these examples actually give you, let me see if I can find a good one. How about this? A few of these examples are actually giving you a response. So this question is, the question from the user is there a cost for Arize beyond an annual subscription price? The response is, Arize offers different subscription plans to choose from depending on your needs. However, there may be additional costs associated with using certain features, et cetera, et cetera. So it's giving what sounds like a pretty confident response. But here's the catch. If you actually look at the retrieved pieces of context, the first piece of context says, Arize is an open platform that works with your machine learning infrastructure, et cetera, doesn't have any information about cost. The second piece of retrieved context is, Arize supports full role-based access control using organizations and spaces, et cetera, also no information around cost. So it turns out that this particular response is actually a hallucination. The chatbot in this case is actually just making stuff up. We actually don't have different subscription plans. And you could imagine how actually having a chatbot that makes up this kind of information could make customer calls pretty awkward for you, right? And this is really undesirable behavior. When your chatbot doesn't retrieve relevant context, you want it to say, I don't know. You want it to say, I'm not sure of the answer. And that's not what's happening in this case. So hopefully at this point, I've shown you how we can help you pinpoint those subjects that your users are asking about where you're getting a lot of negative user feedback. There is one little of a drawback. There is a little bit of a drawback here, which is that to do this, you actually need user feedback, right? You need that thumbs up, thumbs down signal from your users, and you're not always going to have that. Or even if you do have that thumbs up, thumbs down signal from your users, it's not always going to help you pinpoint the exact mode of failure. All you know is the user didn't like the response, but you don't know exactly where in the search and retrieval process did this bad response come from. What part of the search and retrieval application failed? So the next idea I'm going to introduce is this idea of actually using query density in order to highlight broad topics that your documentation does not cover. And this is going to be something you can do even when you don't have ground truth. So to do that, let's go ahead and come back to our display settings and color by data set. So now once again, I'm looking at my queries in blue and my documentation chunks in purple. And if I come up to the metric dropdown, let's go ahead and select Euclidean distance. And what that is doing is now I am, and also select most drift here. Now I am looking at the clusters and sorting them based on the purity of the cluster, meaning the proportion of queries in the cluster versus database entries. So you can see that in this blue bar right here. This blue bar means that this cluster contains all blue data points, all query data points. And why is that a problem? It means that we actually have this cluster of queries out here that is really far away from our knowledge base. The embeddings for these queries are distant, different, far away from our knowledge base. And if we actually click on what these questions are asking, it's actually identifying the exact same cluster of questions. So again, we don't have any information about cost in our documentation. And hence what you see is that all of these questions about the cost of our platform, they wind up all the way out here, way far away from any purple data points, meaning that it's kind of out in left field. And again, this method allows you to actually detect questions or areas of user interest that are not covered by your documentation, even if you don't have any feedback signal from the user. Okay, so that was the second story that I wanted to tell you. I showed you how can you use Arize in order to detect areas of user interest that are far away from anything in your knowledge base. But the downside of this approach is that it only identifies really broad topics, but it's not going to show you the small little gaps, right? Sometimes, you might have a topic in your knowledge base that is covered by your documentation, but you might be asking a really very, very particular question that isn't answered on that particular piece of documentation. So now let's start thinking about, like, how can I get something that's more fine-grained, that's going to really help me pinpoint the cause of failure for individual queries. And one first thing that you might try in this situation is you might try something like cosine similarity. You might think, oh, well, hey, during that retrieval step, we are using cosine similarity as a heuristic in order to retrieve documents. So maybe I should expect that the documents that I retrieve that have a high cosine similarity with the query embedding, maybe I should expect those documents to be highly relevant or good retrievals. And conversely, maybe I should expect documents that have a low cosine similarity with the query. Maybe those ones are not going to be very relevant or not going to be very good retrievals. And it's going to turn out that this is a little bit of a mixed bag. Cosine similarity is going to work in some cases, not going to work in others. Let's actually just dive in, though. So let's take a look here. Back down in the display section down here, I'm going to go back to dimension. And this time, the dimension I care about is context similarity 0. So what this number is the cosine similarity between each query and the most similar piece of context in the knowledge base. And that is the first piece of context that is being retrieved by this particular search and retrieval application. And here in the legend, you can see that the cosine similarity, it runs between the range of about 0.75 up to about 0.9-ish. And again, those are the colors that you're seeing over here in this point cloud. And let's actually toggle off our database entries for a moment. And I'm going to select dimension, and that's going to deselect all the points. And then I'm just going to select the lowest cosine similarity scores here. So now you should see a bunch of purple data points over here. And let's go ahead and take a look at some of these points. All right. So I'm seeing some purple data points. Let's look at this one. What counts against my plan usage? And you can see that the cosine similarity is quite low. And indeed, if you actually look at the question and look at this retrieved piece of context, they're not actually that relevant, right? The question is asking about plan usage, what counts. It's kind of asking a question around pricing, I think. And the context says model performance metrics measure how well your model performs in production. So it's talking about something totally different, and it indeed does have this low cosine similarity score. So that's pretty encouraging, right? And conversely, let's actually look at what the good retrievals look like, what the high cosine similarity retrievals look like. So now these green data points, again, these ones represent those retrievals, those retrieved pieces of context that had a very high level of similarity with the query. And let's go ahead and take a look at this one. So this question is asking what drift metrics are supported in Arize. And you can see the cosine similarity is quite high, 0.88. And this very first piece of context actually answers the question. It's a relevant piece of context. Arize calculates drift metrics such as population stability index, scale divergence, et cetera, et cetera. All right. So the important thing to note here is that this piece of context directly answers the question, and it has a high cosine similarity. But already you're starting to see here that there's a little bit of a gap, just because basically here's the second piece of retrieved context. You can see that it has basically the same cosine similarity score, very, very similar. And if you actually read this piece of context, it says drift monitors measure distribution shift, which is the difference between two statistical distributions, et cetera, et cetera. Turns out this one doesn't actually answer the question, but it has a lot of the same like words in common. It has drift, it has metrics, and those superficial similarities are actually causing the cosine similarity to be high, even though the context is not directly answering the question. And you can really see this if you actually just zoom out here and look at our pricing cluster. And again, this is that cluster that we've been looking at that has all of these questions about pricing all the way out in left field. If you look here, all of these retrievals have to be irrelevant retrievals because again, we don't have any information about price in our documentation, but you can see that the cosine similarity here actually runs the gamut. You've got some retrievals that were really low cosine similarity. You've got other retrievals that were really high cosine similarity. And if you actually look at one of these ones that's like really high cosine similarity here, what you can notice is the question is, what is the cost of the Arize platform? The retrieve piece of context says, Arize is an open platform that works with your machine learning infrastructure. And again, this is not talking about cost at all, not a relevant retrieval, but it has these superficial similarities in common with the query. It's talking about Arize. It's talking about platforms. And it has these superficial similarities that are causing it to have a high cosine similarity, even though that retrieve piece of context isn't really relevant to the user's query. Okay, so hopefully at this point, I have convinced you that similarity is not the same as relevance. And really, the thing that we care about when we're talking about that retrieval step, the thing we really care about is actually whether or not the context is relevant. So the last idea I want to leave you with is this new thing that we're working on, which is the idea of using ranking metrics, and in particular, LLM-assisted ranking metrics, in order to directly measure the effectiveness of the retrieval step. And I'm going to walk you through what that means right here. Looks like I'm running a little bit long on time. Amanda, are we still good? Like, I think I can wrap up in about like 5-ish minutes.
Yeah, you're fine.
Sounds good. Sounds good. So let me explain this idea of what I mean by LLM-assisted ranking metrics. And I'm going to do that with an example. So here, once again, we've got some queries. And again, here are queries about the Arize documentation. This particular query that we're looking at is what format should the prediction timestamp be? So the prediction timestamp it's something you use with Arize, and the user's asking like, oh, like what format should I use for the timestamp? And here are the two pieces of context that were actually retrieved by this particular application. The first piece of context says the timestamp indicates when the data will show up in the UI. And here's the important part, sent as an integer representing the Unix timestamp in seconds. So there you go right there. The Unix timestamp in seconds is telling you the format right there. And here is the actual relevant, not relevant classification. And where did we get this? We actually are going to get this by asking GPT-4, hey, here's a question. Here's a piece of context. Does that piece of context answer the question relevant, not relevant? So we're getting this relevant, not relevant signal from another LLM. And I'll show you the place in the code in the notebook where we actually do that in a second. But let me just show you the second example here to make it more concrete. Again, same query. What format should the prediction timestamp be? The prediction timestamp represents when your model's prediction was made, yada, yada, yada. It's a column. You send it to Arize. This particular piece of context does not talk about the format. And so in this case, GPT-4 correctly says, hey, this is an irrelevant piece of context. It does not address the query from the user. And why are we going through the trouble of getting these relevant, not relevant classifications? Well, the really cool thing that you can do is that once you have this information, you can compute ranking metrics on your query, and you can directly measure the effectiveness of that retrieval step. So there are many different ranking metrics that you could choose from. The one that we're going to talk about today is called precision at K. And in particular, we're going to talk about precision at 2, because for a particular application, we're only retrieving 2 pieces of context. So what is precision at 2? It's just the number of the 2 retrieved pieces of context that are actually relevant to your query divided by the total number of retrieved documents, which is 2. So it's just what percentage of the retrieved documents that I got are actually relevant. That's what precision at 2 is. Okay. And let me just quickly show you, pull this off. Let me just show you real quick where this actually is in the notebook. You can take a look for yourself. We're actually just computing this right here in this cell right here. And all we're doing is we are setting a system message for GPT-4 that says, you will be given a query and a reference text. You must determine whether the reference text contains an answer to the input query. Your response must be binary, should not contain any other characters aside from 0 and 1. 0 means the reference text does not contain an answer. 1 means the reference text contains an answer to the query. Okay, and then we paste in the query, we paste in the context, and we ask it for a response. So that's how we got that relevant, not relevant signal. I don't claim that this is like the exact prompt that we should be using for this particular task. This is just the one that came to mind. But that's how we're getting that relevant, not relevant classification. Okay, so now we've talked about like, what is precision at 2? We've talked about how did we get it? How did we use an LLM in order to get this precision at 2 number? Now let's actually use it. And in order to use it, I'm once again going to come down to the color by, dimension, and select OpenAI precision at 2. So what you're seeing now over here is our point cloud. And let me once again deselect my database entries. What you're seeing is the point cloud. And now you're going to see a couple of different colors. You're seeing purple. Purple means 0 precision at 2. So 0 precision at 2 just means that none of my retrievals were relevant. You also see these blue points, which are going to be 0.5 precision at 2. So a 0.5 precision at 2 means that one of my 2 retrievals was relevant. And the green points are good. Green means that both of the retrieved pieces of context were relevant and that I have a precision at 2 score of 1. Okay. And once again, let's go ahead and select the metric we care about. In this case, we care about OpenAI precision at 2. And now let's go sort our clusters by lowest metric value so that once again, the clusters are being sorted in ascending order by that precision at 2 value. And boom. Once again, we have identified that same cluster right off the bat, which again is this cluster about questions that actually have no grounding, no relevant documents in the Arize documentation. And you can see that all of these data points are purple, meaning that for each data point, in this case, the query is like, do you have a pricing calculator? The OpenAI relevance is irrelevant, meaning that GPT-4 is correctly saying, hey, this piece of context is not actually relevant. Hey, this is a problematic point that you need to look at because the user's asking a question and getting a response for a data point that actually doesn't have context in your knowledge base. Okay, that just about wraps up the presentation. I think we want to reserve a little bit of time just for questions and answers. But before we do that, I just also want to say thank you so much to our partners, LangChain and Pinecone. Thank you so much to Lance and to Kevin. We really appreciate it. If you like the demo, please go ahead and try out Phoenix. Once again, you can just pip install it, fully open source. Consider leaving us a star on GitHub and stay tuned for more integrations because we've got a lot planned for tighter integrations with LangChain and Pinecone. And if you run into any issues with the notebook or run into any issues with Phoenix, please go ahead and join our Slack community. You can ask those questions in the Phoenix support channel, and I will get back to you really quickly. All right. Awesome.
Thanks so much, Xander. Yeah, we have a time for a few questions, but just to reiterate what I said in the beginning, this session has been recorded. We will be sharing it with you guys after the event. We will also share on our social and YouTube channel as well. So let's dive on in. How do you guys feel about domain adaptation, fine-tuning small LMMs to increase accuracy of the vectors?
That's an interesting question. So the question's around like fine-tuning, like when maybe the question is really around like when would you use fine-tuning, right? In what circumstance, right? I think the answer is like I'm not quite certain. I think that like we're still kind of waiting to see best practices around that. Certainly, it's not the first thing that I would try. Like fine-tuning is relatively heavy lift. There's likely to be other areas of the system that could use where I would probably try to improve first. That's my initial thought, though. I don't know, Lance or Kevin, do you have any thoughts there?
I can add something quickly. So I think what Xander just showed is a very nice overview of how to think about this. Remember the flow. We start with documents, we do retrieval step. You get your documents, you pass those to the model synthesizes to an answer. The retrieval step independently can be debugged and should be debugged. And that's what Xander showed very nicely. You can lots of tools to say, am I retrieving relevant docs from my vector DB? So that's stage one, right? That should be independently evaluated. Stage two is take those docs, put them in the context window, use an LM to generate the answer. That's where you might think about fine tuning. If, for example, you wanted answers of a very particular type, if you had very domain specific documentation that required certain nuances in terms of those answers, you might fine tune for that answer stage. But the document retrieval stage should be independently evaluated. And that's what Xander showed very nicely here. So I think fine tuning is definitely an interesting tool on that kind of answer synthesis stage of this retrieval augmented generation flow.
I'm curious too, Lance, because I think this is a really interesting question too, is like, there's another way that you can also try to tweak the output at the response generation stage, which is to actually tweak the system message, right? Or tweak the prompt, right? And
Sure.
That's certainly going to be like probably like less work than fine tuning too. So like, in your opinion, do you think like, do you recommend that people like tweak that system message in the response generation step first, or
Yes.
I guess intuitively that seems like where I would start.
Yeah. Okay. So this is an important point. There's some very nice tweets out there from Travis Fisher. Karpathy's also mentioned this. There's kind of a hierarchy of things that you might try to improve your answer quality. Prompt engineering is like the first thing, and that's the easiest. You should certainly start there. You can also do, I mean, in a sense, when you're providing this context, you're kind of giving the model a lot of information. You can also try kind of few shot learning, where you give it kind of example pairs. Prompt engineering, few shot approaches are certainly advised prior to the heavier weight approach of actually fine tuning a new model. There are some really nice, cool platforms for fine tuning. Mosaic, I know in particular, has done a lot there, but it's certainly a heavier weight than tuning tuning the parameters of your overall chain is another thing. You can tune your chunk size, you can tune your chunk overlaps, you can tune your prompt. There's a ton of things you can do before you get into fine tuning, of course.
Yeah, thanks, Lance. Cool. Hopefully that answered the question.
Great. And if you have any links to those tweets, I think that's something that folks are asking for in the chat.
Yep, I'll add them right now.
Perfect. Now we have a question about hybrid search. Do you have any experience in improving the efficiency of hybrid search methods when dealing with large numbers of legal documents, for example, with the use of search prompt generation? And so while this is obviously talking about legal docs, you can kind of apply that to anything within the same formula, essentially.
Yeah, I'm actually not deeply familiar with hybrid search, and I haven't worked in the legal space in particular, so I'm not sure I'm able to answer that one. But if you follow up with me, go ahead and follow up with me, and we can talk about it more.
Kevin, you
Yeah,
might.
I can talk.
Yeah.
Yeah, I can chime in with a couple of ideas here. So we do have several legal customers who are trying to do things like chatbot style on contracts and agreements and things like that. With respect to actual hybrid search, so there's a traditional way to do it, and that's with your document stores that you may have today, such as an Elasticsearch or something like that, where you have those documents stored. You have lexical search already today. You have the ability to do things like faceting and pagination and all the other fun search engine techniques that you can use with those tools. One thing that Pinecone has done over the last several months is we have introduced our own version of a hybrid search capability. And that hybrid search capability, how it works is not only are you creating your dense embeddings, which is what you're already doing today when you upload your vectors to Pinecone, there's the notion of a sparse embedding. And we also recommend the Hugging Face model splayed. And we are able to then store essentially two vectors, one for the sparse vector, which is the lexical representation, and then of course the traditional dense vector, which is the semantic representation. And then at query time, we do the same thing. Take the customer's query, we could generate a sparse version and a dense version, and we send that to Pinecone. And what you get out of that is a automatically re-ranked result best between the lexical representation for your very specific domain vocabulary, as well as the semantic or the intent of the query that's coming in as well. So it works very well. We've written a really nice paper on it as well, one our data scientists have. And so we're very happy to share that information. In fact, someone asked a Q&A question earlier that I dropped the link on there, but it's I can drop it in the chat here as well.
Yeah, and we have a ton of really great resources in our Learning Center on our website, so I highly recommend checking it out. One last question, not super deep on embeddings here, but any intuition on what are common causes of poor retrievals? Common words, clauses, sentences, especially for poor retrievals that have high cosine similarity scores.
Yeah, that's a good question. Okay, so what are the common causes for poor retrievals? I mean, I think, I think part of it really is just like, part of it is I think in these applications we're using cosine similarity, we're using similarity, right? And similarity could be capturing a lot of different things. As you're mentioning, it could be capturing things like what words are there. It could be capturing one interesting thing is it could be capturing like certain things around like the length of the piece of text, or like, is it a question? It could be capturing things around tone, sentiment, right? So the embeddings, depending on what model you're using, it could be capturing all this kind of information. And we're using similarity as a proxy for relevance when we're actually trying to retrieve pieces of context with similarity. But I think really what it boils down to is similarity is just a proxy for relevance. It's not actually relevance. And so we can't expect that similarity step to always perform really well, because after all, being similar is not the same as being relevant. So I guess that's kind of like my intuition there a little bit.
Great. And with that, we are at time. I want to say thank you to everybody who's participated. Really appreciate you guys being here, sharing your knowledge. I've also, for those who are in the Bay Area, on July 13th, we are having a Pinecone Summit centering around chatbots and hallucinations. So if you are out there, I hope you can join us. And thank you again. Round of applause for our hosts.
All right.
Thanks, everybody.
Thanks so much, everybody.
Bye.
Thanks.